Hi, this is the third lecture about mining geostatistics. Well, in the last lecture, we have seen the support effect on the recovery functions of reserves. In this lecture, this is about another important issue, the information effect. Take the example of a grid point of an x0 at location x0. Well, kriging gives the best estimate of the mean value z of x0, a linear combination of the surrounding sample values. Well, but there is a problem that you know very well. Histogram of krigged values are smooth version of real histograms or the real transfer functions. Okay, and and you are going to see how much this smooth effect on histogram transfer function of reserves are affected with the estimation quality of kriging. Okay. Okay, kriging, as you know, kriging is a smooth linear filter. We can put the real value, z of x, equal to the krigged value plus an error, which is the kriging error that you know. Now, assuming the independence between the estimator and the error e of x, which is true in kriging, we can write this expression in terms of variance. The variance of real values is equal to the variance of estimated values, kriged values, plus the variance of the error. There's no cross terms here. Okay, so so we can say about the increase of the smoothness of the histogram of kriged values. The higher is the error, which is the same the variance of the error, the lower is the variance of estimator, more smooth though the histogram of the estimator. So the main reasons of increased smoothness of the histogram of kriged values are related with kriging error, which is the same the quality of the estimates. Okay, so the possible reasons for this the quality of the estimates is spatial structure of the phenomena. As you know, more random structure, high negative effect, lower variogram ranges implies high errors and lower variances of estimated values, poor estimates. Okay, another fact could be the lack of information. Lack of information leads to poor estimators, and you know that. Lack of data implies high errors and lower variance of estimated values. Information, we can say that the information effect is the influence of the amount of data, of information we have in the transfer function estimators. Okay. Let us see one simple example represented in 2D. So this is let's consider our real mineral deposit represented here. Okay. And now we are going to take from this model, we take two set of samples. First, we take 30 samples, the set of samples number one, and second is the the second set of samples with 100 samples. Okay. Now you can see the statistics of the real deposit or body, and statistics of those the 20 samples and 100 samples. More or less the same, identical statistics in both set of samples. Okay. Now let's do this exercise. Now let's create a Krieged model with the first set of samples, which is same with the 20 samples. And this is the Krieged model. Okay, we can see that it succeeds to reproduce some parts of the real situation, but miss others, like this one and this spot and this one low value spot and so on. Now let's do the same with the second set, the another sample set. Okay, and you can see that this is a more rich representation of the reality. All these red spot areas are represented, the blue also, miss some of them, but this is the best we can do with 100 samples. Now let's see the statistics of the reality, the real body, and the two models created by 20 samples and 100 samples. As you can see, the mean is about the same in all, is about this in the reality and in both models. But look at the variance. The variance is of the reality is 37.5. The variance of the values, estimated values with just 20 samples, is 8.7. And look at the variance of the second model is higher than this one, of course, because it's better estimated, but lower than the reality. Now, in those maps, for each real value, for example, in each pixel, we have an equivalent value, the estimated value. You can take all those pairs and create this B-plot, the real values versus create value, estimated values. Okay? And this is the B-plot of those two models. Now let's see what happens to the extreme values. What are the values under, for example, 6%? Okay, this is, let's consider this cutoff, a lower cutoff. And we can, if you want to see the values under 6%, you can see that the estimated, this is the estimated value, script value. You see that under 6%, this, all those points are considered lower than 6%. But if you look at the real values, in reality, the points lower than 6% are those ones, are this cloud here, which means that this upper part of the cloud here, 81% of the values under the cutoff are overestimated by Kriging. Kriging consider those values higher than 6%. Correctly estimated, you can find just 19%. Okay, let's see what happened in case 2 with another samples. It's a little bit better. Okay, you can see that we have only 70%, 71% of values under cutoff grade are overestimated and 29% correctly estimated. So if you compare both B plots diagrams, we can see that with the second case, we are talking about extremes, right? In the second case, we improve a little bit better, but that's again, we only have 29% of correct estimates of values lower than 6%. Okay. Let's see the other extreme, high cutoff, which is 20%. Let's see the values above 20%. If you want to see the values above 20%, you go to the estimated, and you see this above 20%. You can find those, just those ones here. Okay. But in fact, in reality, the values above 20% are those here. which means that those ones here, 79.4% of the results above the cutoff are underestimated. And this portion here, upper part of this cloud, 20.6% are correctly estimated. Let's see in the second case with the 100 samples improve a little bit better. We have 73% of underestimated values, and just correctly estimated we have only 27%. So compare both. You can see there's some improvement, but still the cloud is a little bit more according to the diagonal and so on, but it's still poor for extremes. If you look to the creep values to get the extremes, both are poor. So in short, kriging of the original variable z of x is a good estimator of local means, but it is a bad estimator of local variance and histograms. Let me remark one thing: is the best estimator of local means because it was with that purpose that was built to reach the local means. It was not built. Kriging was not built to reach local variance or histograms. So when you use kriging of the original variables to calculate recovery functions, one must account on the smoothing effect, of course. For example, let us see the effect on transfer function. Now, tonnage recovery functions with the ZC above a cutoff grade ZC. Now, the tonnage is calculated with the set of an estimated values. We have learned in the previous lesson the definition of tonnage on real values, the real tonnage. But here we calculate the recovery function based on estimate. So it's the same expression, so it's the average of indicator function, but the point is the indicator function, it takes the value 1 if the estimated block value is greater than ZC, otherwise it's 0. So we decide based if a given block is waste or ore based on the estimate creep value ZV. Okay. So the decision about whether a block is or it is not above a cutoff grade is based on the estimate creep value ZV, after the estimated, but the real recovery is obtained on the real value ZV. Because in fact what is going to feed our dressing plant are the real values. What we wish to calculate here is this conditional probability of the real values to be greater than a cutoff grade, given or conditioned to knowing that the estimated block value is greater than a cutoff grade. So in fact, we can see the blocks classified as ore, and that in reality they are not ore. The blocks classified as waste that are in reality are not waste, and so on. And those blocks here, you are dealing with the lower cutoff. Okay? Blocks classified as ore, and in reality they are ore. These are correctly estimated, this cloud here. So the way to minimize, in short, the way to minimize the information effect is to get a better estimates using more sample data by integrating different types of data. This is the last useful message that I would like to tell you. Now let us finish finishing these lectures showing you another way how to deal with support effect. Let's coming back to the first slide. And we are going to see how much this smooth effect on histograms, transfer functions of reserves are affected with the estimation of quality of kriging. Kriging, again, gives the best estimate of this point here. Now, this is the challenge. We start by a problem, now we finish by a challenge. Access local histograms of values, z of x, point values, block values, to characterize the local uncertainty of resources estimated and transfer functions. Okay? So, and what we are going to learn in your advanced course of geostatistics is an alternative model of resources evaluation, the stochastic simulation. This is as to say, instead of reaching an average model with kriging, stochastic simulation gives you an ensemble of models of the physical phenomena with the same variability and spatial continuity as they are revealed by the experimental data. Those set of models, and as much as you wish. So with the simulated models, you are going to learn that in your advanced course. Simulated, you can access the spatial uncertainty. For example, take the value of the same pixel of the n models here, and you can build for that pixel location the most rich statistics that you can imagine. Histograms, mean, median, variance, percentiles, and so on for that specific location, and for any location, any local spatial location, and so on. Or you can average the values on any support like this one and build equivalent statistics on block support based on stochastic simulation models. Okay, that's all I had to tell you in those 3 lectures, and I really hope you enjoyed the classes of advanced geostatistics. Thank you.